Hello everyone, this is Shomo from University of Texas at Austin presenting our work on finding Pareto trade-offs in fair and accurate detection of toxic speech. Toxic language detection in social media prevents risks of hate speech, cyberbullying, and discrimination against individuals or groups. When training classification models, we often optimize it for an overall measure like accuracy. This protocol often ignores group-specific performances, where the statistical majority performs better at the cost of the statistical minority. This raises concerns of algorithmic fairness, especially around disparate impact across groups. For example, on the Davidson hate speech dataset, we can see that there is a discrepancy of around 6% between the statistical majority versus minority groups when the model is optimized for overall accuracy. This pattern consistently exists over different neural models. The results indicate the need for a fairness level loss function. However, fairness evaluation measures are often post hoc and probabilistic in nature. As such, although they can be used for model evaluation, they cannot be directly used for model training. Another couple problem is selecting the appropriate trade-off between model accuracy versus group fairness that stakeholders can deploy. Our work attempts to address this fairness challenge with respect to NLP models for toxic language detection using two parallel approaches. First, we develop a differentiable fairness measure called group accuracy parity that optimizes for balanced accuracy across groups. Second, we use a multi-objective optimization tool called hypernetworks to trace out the full Pareto front between competing objectives and map out the full trade-off space in one run only. Accuracy parity is an existing measure in the fairness literature that ensures minimized disparate impact across groups. Accuracy difference, or AD, is defined to measure the deviation from this ideal condition. However, AD is probabilistic in nature and cannot be used to optimize any gradient descent-based models like neural networks. Using arbitrary losses in this case can often lead to metric divergence. AD also has negativity issues. Weighted cross entropy is a binary cross entropy variant that reweights for label imbalance within a group. Our proposed gap loss is designed as the cross entropy difference between two groups. From the formulation, one can notice that gap reduces to zero when the errors across the two groups are the same. Gap has the following properties: one-on-one correspondence with AD, differentiable nature, no negativity issues, and the smooth loss surface. One way to find trade-offs in traditional machine learning is to add the fairness term as a regularized loss. This is called single objective optimization, or SOO, where for each value of lambda, we get a different trade-off between objectives. An equivalent multi-objective optimization formulation, or MOO, allows for a linear trade-off between the objectives. Hypernetworks allow us to map the entire trade-off space in one run corresponding to all feasible values of alpha. This improves model training time, all the while giving stakeholders a full view of the trade-off space. So given a neural classification model which takes in data X corresponding to labels Y, the hypernetwork acts as a supervisory model, adjusting the weights of the classifier to learn different trade-offs between accuracy and fairness. For experimentation, we use two datasets: Davidson, where the groups are demographic identities of author groups, and Wilds, where the groups are demographic identities of target of post. For Wilds, although we make a simplifying assumption about the binary nature of target groups, we do acknowledge that gender is a non-binary and fluid construct. For comparison, we use two recent fairness-guided loss functions, all of which has an overall error and a group fairness term added to it. As discussed earlier, when just optimizing for an overall measure like accuracy, without considering group attributes, classification models often get biased towards the group having statistical majority in the dataset. Accuracy difference, or AD, is the measure of the discrepancy in group performances. When we keep the same neural model but instead optimize it for group fairness only, we observe significantly lower values of AD, or group level discrepancy. Since our gap loss is explicitly designed to minimize accuracy deviation between groups, we observe gap to have the least AD. Results shown here are over 5 runs. In practice, we would want some balance between the two objectives. Here we show the model trade-off as the tunable trade-off parameter alpha is dialed from 1 to 0. 1 indicates optimizing just for overall measure, while 0 indicates optimizing for just group fairness. While we do lose some overall utility to incorporate group fairness, we see that GAP does the best job for minimizing disparate impact across groups. For the wilds dataset as well, we see GAP performing best amongst the other two losses for minimal drop in overall utility. We are grateful to the IConference reviewers for their feedback. We also thank our amazing sponsors for supporting this work. Thank you for attending this talk. All our code base and benchmarks can be found in the GitHub URL. Thank you again.